Okay, I slightly changed my title of the talk about changes in ocean circulation across timescales and some insights from data and models. To start with instrumental data, and this is a sea ice fraction in the Arctic and temperature at high latitudes, northern high latitudes on the Antarctic. You see that there are different trends in the northern and southern hemisphere. And also you see so declining sea ice and some increase in sea ice in the last decade. But we see also missing data, basically missing information of sea ice and in Antarctic, around Antarctica and in the Arctic Ocean. And I call that the climate dilemma. So the records of direct temperature measurements are short and fall already in the face of strong human influence, and the data are sparse. And for the time before the instrumental records, one has to rely on information from long-term, often proxy data and modeling. And I will show you in the talk that really the combination of the different timescales matter. So if I start now for the recent climate, and I see the shift in ocean temperature in the North Atlantic in the 70s and 80s. So there was a cold phase in the North Atlantic, and before that time there was a warm phase in the North Atlantic. And this is, if you see the pattern, you see there's the overall large-scale cooling in the northern hemisphere and slight warming in the southern hemisphere. We see that also the signal in the intertropical convergence zone in the Sahel precipitation. Also during that time there was less precipitation in the northern hemisphere in the Sahel region. And if you look in more detail, you can see also this kind of seesaw or multi-decadal mode that we have experienced a cooling in the northern hemisphere accompanied by a warming in the southern hemisphere. And then at the same time here on the right-hand side, the plot in the 80s, there was a strong warming since the 80s, there was a strong warming in the northern hemisphere, especially in the North Atlantic, and a cooling in the Southern Ocean. And this, I think, is kind of a proxy also for the meridional overturning circulation in the Atlantic. In the morning, I've learned, thanks Pascal, that there is a good correspondence of AMOC and this temperature index, but there are of course also differences. This is on shorter time scales of variations in AMOC and North Atlantic climate, but of course on long time scales we saw also in the previous talk, we experienced a strong fluctuation in Greenland. And you see a North Green ice core, but also the forcing, I converted to watts per square meter. Annual mean shortwave radiation is in the range of 4 watts per square meter, cooling and warming, but also CO2 is in the same order of magnitude for glacial, interglacial, but we expect in the future, of course, unfortunately, higher variations than in glacial, interglacial times. So that is basically short-wave radiation and the long-wave radiation, which is strongly affected by CO2. And we expect that these changes, these abrupt changes seen over Greenland, are related to the AMOC change, so the ocean circulation changes. I think that was the great metaphor of the conveyor belt. So it's more like a metaphor, not really a model, I would say. But I think it helped because conveyor on and off, or even reversed, that was the invention. It was the metaphor which brought climate scientists forward that we have stopping ocean circulation or not. And that, if you look in the literature, this metaphor went through a very typical phase of a typical metaphor. That somebody from outside came with an idea, typically not a person who's, in this case, an oceanographer. He brought this idea, and there were also contradictions, and people now try to make that better. But it's a metaphor which created our idea of stopping or even off and on mode of this conveyor. These climate instabilities are not excluded in the future, since we don't know where this climate instabilities, so this high variability in Greenland comes from, and the representation of the feedbacks are necessary in climate models. So in most of my slides, I use a climate model, and it's a typical climate model with atmosphere, ocean, sea ice. Some is also coupled to ice sheets. But the ocean component is something special. You can put the resolution where you like to have the resolution in. And this is an example for the pre-industrial times, early Holocene and the LGM. And you see that you can put a number of nodes or high resolution at the coastal sites, at high latitudes, because the high latitudes have a different dynamics. So we put always more effort on high latitudes, and also on the coastal sides, because there also the music plays in terms of ocean adjustment processes and so on. And we can look at the mechanisms on decadal to multi-decadal on millennial timescales. And I start first with a short timescale, and it's the last 50 years basically. This model is also is a higher resolution version of this ocean model. It's forced by the atmosphere, but I want to point out here this so-called great salinity anomaly event, which is around 1970. And I showed you earlier that this was a period where the northern Atlantic was experiencing cooling. And in the upper graph, you see the salinity. So indeed, at that time, there was also a lower salinity in the surface layer, but in the deeper intermediate layers, there was more salinity. And I would like to point out also in temperature, there was a cooling, but there was also strong warming at the intermediate levels in the ocean. And you see there are several of these salinity anomaly events also in the 80s. And from time to time, we have also strong convection and deep water formation. And then the whole water column is going to be cold, like in this period in the 1995. So what is important, what I want to point out, is in the vertical that you have a cooling in the surface, and in the subsurface there's a warming. I will come to that feature back again. And also accompanied by these changes in the 70s, we have also different large-scale circulation in the gyres. So we have a weakening of both the subtropical gyre and the subpolar gyre by several sphere drops. And going along with this weakening of the gyre circulation, we have also weakening of the amok circulation. And this is the short time scale, and I will come now to a longer time scale. Deglaciation and climate, and Luc also pointed that out, that is kind of puzzling for the sequence of the Heinrich event. So time goes from right to left. Heinrich event, which is cold climate, then to the Bölling-Alleröd, which is a warm, and then coming back again to cold climate, and then again switching to the warm climate. And the upper panel shows the meltwater flux. It's an old graph, but basically it's more or less correct. So during the warming phases, or prior to the warming, we had meltwater coming from the ice sheets. And this is a puzzle because strong meltwater input should weaken the overturning circulation and should cool the climate, so the opposite what you see. And you see in some simulation studies that people just shift this meltwater pulse to the Heinrich mode and then invented negative freshwater into the North Atlantic in order to have this Berlin-Ullerud warming. So that is somehow questionable, but it's maybe seen as data assimilation in the literature. So what do we see if we make this in models? So again, ocean circulation model coupled to atmosphere, sea ice model, here a fixed ice sheet. And the LGM climate looked reasonable well. What we think, okay, cold North Atlantic, salinity has maybe here a small tongue at the eastern side of the Atlantic. Interestingly, mixed layer depth, so the mixing areas is also more on the eastern side of the North Atlantic. And you see here this high resolution simulation because you see really the velocity at the boundary. So what will happen to such a climate system? First, I would like to show you what is the deglacial hosing. So what is actually the input from if you look at ice sheet modelings or reconstructions. And there are two components of deglaciation, namely we have calving, so that is a solid ice, and we have runoff, which is melting, so liquid. That plays a big role, of course, because the calving component is transported over the North Atlantic as icebergs, iceberg armada in the North Atlantic, whereas the runoff goes directly to the coast. So it's quite different. And the meltwater pulse 1A, so that is a peak here, this reddish curve, that's really meltwater because there was a warming and then there's a meltwater. Prior to that, there was a strong calving events, the Heinrich event, which comes from solid. Now, that's a sensitivity study. Now, let's start with this glacial ocean. Actually, the number is probably much too high in terms of overturning rate, but this is as many other models, it's probably completely overestimation of the mean background state. If I do a hosing in different areas of the area around the North Atlantic, namely in a subpolar area, which is the reddish curve, the subpolar area brings also the sea surface salinity to very low numbers, and that mimics the carving of solid water and transport on the North Atlantic Ocean, melting there and make the sea surface salinity low. However, if you have just the melting at the coastal sites, so for instance in the Mississippi region, the effect is very minor because in this high resolution models, this is basically trapped. So freshwater is not so much spread into deep water formation areas, or in the Arctic Ocean the influence is also less. So it matters where you bring your fresh water and whether it's more mimicking a liquid or a solid. And this is, of course, calling for a model which has also icebergs in it. So icebergs are not considered in climate models until now, at least not in a coupled model. So that's a big problem also for present-day climate. Somehow it's in inconsistent energy. Also in the Southern Ocean, people have precipitation minus evaporation. Over Antarctica is brought as runoff to the ocean. That's typically done in climate models, which is a huge error also in the energy balance. Okay, what happens with the temperature? And here I want to point out, basically we see the effect of a shutdown or the weak overturning has a similar feature, namely always a cooling in the North Atlantic and a warming in the deeper levels or subsurface levels. And this is, goes through all models which I've looked at. It's a very robust result. And I think it's key. It's actually very similar to the feature which I showed earlier for the recent climate, for the great salinity anomaly, that there is a vertical gradient in temperature, cooling at upper levels and warming at intermediate levels. And coming now to another compilation of data, so freshwater flux, sea level, North Grip, SST in the North Atlantic, or AMOC proxy. Also, we saw that also in a previous talk, the global mean temperature. This global mean temperature is also interesting proxy, namely it shows that there's a strong increase in temperature prior to the onset of the AMOC. Now, we made a modification of this hosing experiment, namely we keep the hosing ongoing. So we kept this hosing on, and what happens, and this is, I think, very interesting, if you made this hosing about 0.1 Sverdrup in a particular area in the North Atlantic, of course we have a weaker circulation, maybe more realistic for Heinrich, but then with the continuous freshening, there's this strong overshoot, showing also here, and then we are going to a new steady state. So what is happening there? During this Heinrich event, we have a surface temperature which is pretty cold. The subsurface is getting warmer and warmer, and the difference in temperature is that the subsurface accumulates more and more heat. And this accumulation of heat in the subsurface leads to an instability, a vertical instability. Since warmer water is lighter than colder water, there comes a phase in this transition where the vertical water column is unstable, and then the overturning sets in. So that is basically another explanation for the Bölling-Alleröd transition, that this Heinrich mode is inherently unstable. Yeah? You put fresh water into the system, and then leads to heat accumulation in the subsurface, and then there is a vertical instability. And you can also then look at this time series in the model, and indeed there is this overturning, this AMOC strength, but here's also then the global mean ocean temperature, which is increasing. Maybe not as much as in data, but this is also a much shorter experiment. When you look at the other data, we see that this is a pretty old paper, almost 20 years ago or so. But we also found that in other data sets that we have a subsurface temperature warming in the Atlantic Ocean during phases of the Heinrich I and the Younger Dryas. So that seemed to be a very robust feature, and how can we explain that, actually? That's my explanation. So basically we have a balance between diffusion and advection. So advection brings cold water from high latitudes and to the lower latitudes in the deep. And then we have diffusion coming from top, and this balance somehow in equilibrium. However, if we have less advection from the north, then diffusion wins, and then the thermocline changes, and then we have an accumulation of heat. Yeah, that's the idea, that the cooling part due to advection is missing. So what are then, I think this is a relevant feature also for future climate, and we'll come to that in a couple of minutes. What are then the typical challenges? And I think in the morning it showed that there are some challenges also in this long-term AMOC dynamics. There are multiple challenges, and I will shortly touch them, what I think is relevant. This MIS3, so the period where we have the strong oscillations or variability is of course a target, and it's even not known what is the sea level and what are the feedbacks in the system. And it in some studies is shown that the climate noise influences the mean sea level, or that the astronomical parameters during that time are responsible for an instability of the system leading to oscillations. Coming now to future climate and basically taking the same model but now with interactive ice sheets. So that's a forcing on top with CO2 and aerosols and volcanoes. And then on the bottom you see the temperature. So a typical result of many other models, but here is with Greenland ice sheets. What we did now, continue this experiment also in the future for next couple of 100 years. And in the bottom right, you see also temperature. It's still not in equilibrium. So if we keep the atmospheric CO2 concentration in this model at the high level and don't go again to lower levels as in your talk, we still see that there's not an equilibrium. The climate still warms up. What is the influence on AMOC? That's the black line is the PI control run. It has some variations, and the overturning goes down. The reason is, again, warmer climate leads to less mixing at high latitudes, but it's of course more complicated. What happens is here that the overturning is coming back. Usually in all these talks, you stop at the year 2100. So it looks as there's a real decline forever, but it's not the case. There are also stabilizing effects for AMOC. One effect is that is in one of this paper is that the warmer the climate, also the sea ice is gone in the Barents Sea. And then the precipitation minus evaporation changes strongly, and this leads also to stabilizing effects, at least in our model, on long time scales. But what is also interesting to look at is what is happening with Greenland. So Greenland also matters because there's a change in the ice sheet, especially at the boundaries. There's a melting, and in the middle there's more accumulation. So I think this is a direction to go, to look also now not only for higher resolution models, but also include more components in the system. What we heard today in the morning was going in this direction, but on the other side, we have to acknowledge that we have also other feedbacks in the system which are not considered to be in our present climate models. Another feature is also for another really thing, and also we work together with Guillaume Leduc for 10 years or so, looking at ocean circulation changes also for the Holocene for the last 6,000 years. It was really puzzling, what has puzzled us, that we see a cooling, strong cooling at northern latitudes and a warming at low latitudes, according to the astronomical forcing. So the pattern is more or less okay, although there are questions, of course, but the magnitude is completely off. The magnitude is a factor of 5 off. So the data in sea surface temperature, Iconor data, is really showing a much stronger cooling trend for the Holocene than the data. And what is a possible solution for that? So what I did, we made this exercise taking available model runs for PMAP2. So this was a low resolution, 3 degrees resolution approximately, then PMAP3. Gives the same result, also the greenish colors, so slight cooling and only weak warming in low latitudes. And then we had this very high resolution model, and that gives us more heterogeneity in temperature. And what is and even if we downscale this, so bring it even higher resolution, that brings us interesting patterns, and these are shown here. Namely, if we really resolve the western boundary currents, then we have the possibility to have stronger cooling or warming in under such long time scales. So this is unlike what people think, that the longer the time scale, the weaker is the signal on smaller time scales. So it's not a diffusive energy balance, or so that also long time scales can maintain large gradients, and that is due to the special feature of the ocean to have western boundary currents and things like that. So we have heterogeneous trends in the ocean. If we look further on this data and compare to models, it's also in the same way, and this is shown here in the climate spectrum, that the Alconon data and the other data the variance is completely off to the climate models. So it's also orders of magnitude that data is really and show much more variability than the climate models. This can be explained somehow by the Hasselmann climate model. He got this Nobel Prize for that last year. So he wrote down basically a very simple equation which was known in physics, theoretical physics for a long time, more than 100 years, is that we have a damping of temperature, we have noise in the system, and we have external forcing. And we can solve this equation on two ways: ignore the forcing, then we have only the damping effect on the noise, then we have a power spectrum like that, it's a red noise power spectrum, or ignore the time derivative here, ignore the noise, we can cancel out the noise, then we have a response of temperature to external forcing. And in both cases, it shows that lambda, so basically the band, which the relaxation is basically too strong. So the response is too low, the damping lambda is too high, and this is called in physics fluctuation dissipation theorem, that fluctuations and relaxation are related. So I think this is interesting to have that known. What is then on shorter time scales challenges for AMOC? This is actually my link to a shorter time scale like weather, and I think it's also important to consider that the statistics of weather may also affect AMOC. Here's a typical blocking situation. Here you see this omega shape over Europe. A specific day in the 70s, and this is a so-called blocking situation. Usually in summer, then we have very nice weather, then we have stable weather and sunshine. And the question is, we can count now the number of days when we have such blocking, or we can look on the statistics of these weather events, or the frequency of these events. And what we found out that the Arctic sea ice export from Fram Strait, so Fram Strait is here in the north, that highly depends on the blocking, whether we have less or more blocking. So whenever we have more sea ice export from the Arctic Ocean, we have less blocking events here around Fram Strait and Iceland, but more here on the south. Whereas we have low sea ice export, we have more blocking, which is understandable. If we have a high pressure, the sea ice cannot go past that. And this is interesting because this synoptic scale variability on decadal timescales, so the frequency of blocking, has an influence on AMOC, namely whenever we have more fresh water entering from the Arctic Ocean, we have then, with a certain time delay, here prior to the 70s, we have more sea ice export and then these freshening events in the North Atlantic. So this indicates there is a linkage of short-term variability to long-term variations. This is also a challenge for long time scales, centennial to millennial time scales. If you look at Greenland, and look at the waiting times between these Greenland ice core warming events, they are completely random. They are Poisson distributed. So there is no clear frequency behind that. And this is, of course, a challenge because the climate models, if they have variations, they don't have this fluctuation. But I've looked at colleagues' results, and I found a result where they found these oscillations in the Labrador Sea for centuries in their control simulation for present-day climate. And but they said they don't want to have these oscillations for our present-day climate. That's a mixed layer depth. Here's 1 kilometer and 0, so it fluctuates really a lot, and it's also stochastic in nature. But this is now absent in the newer versions of the RV climate model. I'm a little bit I'm astonished about that because in principle we need also variability in models, also in order to explain like variations like the Dilted Ice Age or medieval warm period. So I think not wanted is questionable. It's also highly depends on the resolution. So this Labrador Sea convection does depend on the resolution. So here the reddish lines shows a high resolution run, whereas the lower is a low resolution, and in the high resolution runs we are able to have really variability of the Labrador Sea convection. So that depends, I will not go into detail, but this depends on the process of restratification of the eddies, what we have heard in the morning. So that is basically what I wanted to say about that we have a linkage between the time scales, so the synoptic variations, also they feeding to longer term variations like the Atlantic multidecadal oscillation, like this Greenland Great Salinity anomaly, which is somehow in a way similar as the Dansgaard-Oeschger fluctuations which I showed for long time scales. Yeah, other perspectives I think are for AMOC are also clear because we need now truly coupled model for the LGM and for PI, so really coupled with ice sheets. This is what we found out now in a bigger project in Germany. For LGM, for instance, look like that. It's too much ice actually here, but it shows a weaker overturning than in the uncoupled run. The reasons I don't understand in detail, but it's of course a new direction of research to have a coupled ice sheets now. And also to study multiple equilibria. So I mean, this is the other Nobel Prize winner, Manabi and Stauffer here. Manabi, I think he was one of the first one who claimed, or actually, that there are multiple states in the system that we have. With the present day climate, we have the possibility to have an on mode overturning, looks like that. Actually is the other way around. Here is north and here is south. Or we have an off mode in that. What is the future direction? How realistic are models? And I think we are now in a very fortunate situation. We are developing into a system which is comparable to observations. So this is for a CMIP 5, so a model intercomparison project 5 phase. This is a higher resolution for the high-res MIP, was also mentioned in the morning, higher resolution. These are the satellites, ocean circulation can be traced by satellites, and this is a very high resolution model. So, and this shows that we are now approaching somehow realism in ocean models. And of course that comes also with a price, but I think the price is not so high since these old models have large uncertainty in regional changes and in extreme events like heat waves. The good thing is that the good climate models, especially in the ocean, are scalable in a way. So if you have more cores or more computer resources, then the model is also faster. And this is shown here for our particular model, but I think most people are working on that now. If we have more computer cores, then we are able to have, even for high resolution runs, we have maybe 60, maybe 100 years a day for high resolution models might be possible in the future. So our present day or present science is limited by available high performance capabilities, computing capabilities, but probably in the future our limitation is due to the ability to use the high performance computing capabilities. So it's a shift. Basically, in the future we need to know how to use the computer resources. And the hope is, of course, that these processes, which are not represented by the laws of physics, but more by the rule of thumbs, so these so-called parametrizations are not necessary anymore. That's a hope, I don't know, but this will hopefully reduce the large uncertainties in regional and probably also global climate projections and limitations of saying something about extreme events. Just mentioning tracers, of course, such high-resolution models have the ability to really simulate tracers like carbon 14 in the ocean. And with this, I would like to summarize it. So, AMOC variations on decadal to centennial timescales are related to this mid-depth ocean warming. That is both true for decadal and a very long time Heinrich and Bölling-Allerød sequence. There's I call it now self-destroying off mode. So there's a heat accumulation in the off mode, and this destroys the off mode. That's, I think, pretty interesting. I've shown you also that long-term climate variability is underestimated in models, but eventually one has to really think on detuning the models. They may be tuned too high in order to avoid such variability. And these heterogeneous trends on long timescales, they depend on the resolution and also the ability of simulating blocking events in the atmosphere. Thank you very much.